Okay, this question says, sketch band diagrams for a metal, insulator, and semiconductor materials. And then part 2 says, how would dopants modify these band diagrams? Okay, let's get started. So with a metal, we know about a metal is that they conduct electricity. The reason that they conduct electricity is that they both have carriers, right? And they have spots for these electrons to go as they hop through the lattice, right? So let's start with their band diagram, right? Let's say that that's one of the bands in this structure. The Fermi level corresponds to the energy level at which you would fill this band level up if you were at 0 Kelvin, right? So if you cool this thing down all the way down, your electrons are going to occupy some energy states, right? And if they occupy all the way up to that level, we call that the Fermi level. Now, because this is a metal, the Fermi level lies in the middle of the band. What this means is that if you apply an electric field to this, electric field is something that's going to cause these electrons to want to move. They can occupy any of these states up here. All of those are empty states currently, so those are able to be filled, right? Now, so that's a metal. How does an insulator and a semiconductor look different? Well, an insulator might look something like this, where you have down here what's called your valence band, and up here you have your conduction band, right? And the Fermi level is going to lie somewhere in the middle still, right? Let's label this again as our Fermi level, EF, right? Now, because you have your states completely filled in your valence band and completely empty in your conduction band, there's no empty spots for electrons to hop, right? So in the case of a metal, you got conduction because your electron, if you temporarily move this one up here, you could put it in one of these sites, right? But that's not the case over here because these are completely filled and there's nowhere for them to go in this big energy difference between them, which we call the band gap, E sub G, right? So the only difference between an insulator and a semiconductor is the size of this band gap. In a semiconductor, it's typically small, something like 2, 3, less than 1 maybe. It's on the order of electron volts, but it's small, whereas an insulator might be 3, 4, 5 electron volts, right? The band gap is small here in a semiconductor. What that means is if you heat this semiconductor up, you can take electrons out of this valence band and they can get thermally excited to occupy the conduction band, right? So this electron that's down here, it can get promoted up to the conduction band. And now that electron in the conduction band has lots of empty seats where it can move around from. And moreover, it creates what we call a hole in the valence band, which is essentially a spot where an electron can hop. So nearby electrons can jump into the hole, thereby creating a hole where they used to be. So you can get conduction both in the conduction band and the valence band. So when we dope these things, how do we modify them? Let's just look at the semiconductor when we talk about doping. How does it change? As you dope a semiconductor, let's say that your lattice is originally silicon. Silicon always has 4 electrons, right? And that's why when it shares with other silicon atoms, this one has 4 electrons, they form a bond, 2 electrons, right? Now if you put something like a boron in there, boron only has 3 electrons, right? So you've got bonds between all these things like normal, but right here you have a missing electron, right? So what can happen is one of your electrons from elsewhere in the lattice, it can hop into this hole, it can temporarily occupy that bond, but in doing so, boron normally only wants to have 5 electrons, but by adding 1 more, you've given it an extra electron. You've created a boron minus ion, right? You've ionized the boron, you've given it an extra electron. So that does cost energy. The boron doesn't want that extra electron to sit there if it had its druthers, but it's not a big penalty either. Now we can go the other way. Let's say over here you had a phosphorus, right? A phosphorus normally has 1, 2, 3, 4, 5 electrons, right? So if you've got a silicon down here with its 1, 2, 3, 4, all of a sudden you've got this extra electron, right? That extra electron, it's not involved in bonding, and so it can be stripped away. It could be pulled away, leaving behind phosphorus that's positively charged. Just like the boron, since it accepts an electron and becomes negatively charged, phosphorus can give away an electron and become positively charged. So both of these are donors, but they look differently in the diagram. For example, if you have a couple boron atoms sprinkled in there, let's put those right here. these would look like states that are close to the valence band, where an electron that's normally down here can hop up and occupy this state, thereby creating a hole, right? That's what we did. When this electron jumped down into the boron, it created a hole right there by filling the hole that was associated with the boron. Meanwhile, up here, these would be the phosphorus states. Phosphorus has an electron that's really a small energy difference, just that much energy, in order to get up in the conduction band, and then it can conduct, right? In both cases, note that the conduction happens through the silicon atom network. The donors are relatively few and far between, but the conduction doesn't happen on their network. It happens through the silicon network because the boron accepts an electron, which creates a hole in the silicon network, or the phosphorus gives up its electron, which puts a free electron in the silicon lattice. And that's how doping would change the band diagram of a semiconductor.